Okay, picking up with observing the sun and the solar system. We're going to look at a history of the sun and the solar system and some of the different theories of how our solar system came to be. So we start off by looking at a geocentric view. This view is an Earth-centered view where we have the Earth in the center of the universe. We're looking at calendars based off of this idea, different constellations would show up in the night sky, and they would say, okay, now that this constellation is out, it's time to start harvesting crops, or now that this constellation is out, it's time to start planting crops, or start preparing a feast, or cold weather is coming, or warm weather is coming. So they base their calendars off of these constellations. They thought the stars were holes in a celestial sphere that surrounded the Earth, and they had this retrograde motion where some of the planets were thought to stop moving for a period of time, perhaps a week or so, and then start moving again, or they're going to start moving in one direction, then moving backwards, and then continue moving again. And we notice this a lot with Mars. Here's our geocentric view where we have the planets in their own little orbits around the Earth. And there was good reason to think that this at the time was the way it happened. You know, it doesn't feel like we're moving while we're on the Earth right now, but we see the sun go across the sky, and we see the moon go across the sky, and we see the other planets move across. So it seems like, you know, since everything else is moving and we don't feel like we're moving, we should have the Earth in the center. We have this video on retrograde motion where they kind of show how the planets move across the night sky. So if we start to look at the way we view something like Mars, we have Mars in red and Earth in blue. It appears like it's moving across the night sky, and as our smaller orbit catches up to that of Mars, it then appears like Mars starts to move backwards as our smaller orbit we pass off Mars. And then it continues to move again. And that's all in relationship to those background stars. Here's an actual time lapse of Mars moving across the night sky, so they give us some reference stars there, and you can see Mars moving from right to left, and then it kind of stops for a second and slows down and goes backwards from left to right, and then again stops and continues back on its path through the night sky. And we can take a look there, and they kind of give us the time lapse on how long that takes. So they kind of say it starts off there in October, and by January then it is starting to move backwards, and then it begins again in March to start moving again across the night sky. Then we looked at Ptolemy. Ptolemy was the first to start trying to predict how the planets moved across the night sky. He still had the Earth in the center, and he looked at what the planets and said that they moved around in small orbits called epicycles. He still, though, could not explain for the retrograde motion and why the planets would appear like they stopped moving at different times in their orbits around. Then along came Copernicus. We're looking at about 1,000 years or so difference between these two. So for a long time, humans thought that they were the center of the solar system and the universe. And then Copernicus came along and said, if we put the sun in the center, he developed this heliocentric model that predicting the planets became a lot easier. So everything in our solar system revolves around the sun, and that's the current model that we use today. So here's our difference between the heliocentric model, helio standing for helium, and that's what's inside the sun, so that's why it's the heliocentric model. And again, sun in the center, or the geocentric model, where we look at geocentric, geo, earth, geography, geology, and we think of that, the earth then centered model. Next, we're going to look at Tycho Kepler and planetary motion. The discoveries here with Kepler and planetary motion are going to be that these planets are going to move around in ellipses and not perfect circles. And they had three laws to go along with this planetary motion. So the first law is that the planets travel around in the elliptical orbits with the sun not at the center but at the focus. So they're orbiting around the sun, but the sun isn't necessarily in the center of that orbit. The second one is going to be the equal area law, and that's going to allow the planets to move around in such a way that an imaginary line adjoining the planets to the sun sweeps over equal areas of space in equal periods of time. And the third one is the harmonic law, where we look at the time it takes a planet to travel around the sun, and we find that it's got a relationship to the distance that the planet is away from the sun. So the time it takes to travel around shows a relationship to the distance, or the average distance that the planet is from the sun. So with Kepler's law here, with the first law, we're looking at not a perfectly circular orbit, but an elliptical orbit. And again, not with the sun in the center, but at the focus. It also shows here that the planets are going to slowly speed up and slowly slow down as well. So there's going to be these slight changes in the speed of the planets, and that's going to help explain some of the other parts of Kepler's laws. But when we are closer to the sun, we're going to go a little bit faster, and it's going to give us that slingshot motion. And then when we're furthest from the sun, we're going to slow down a little bit in our orbit around. Now these gradual changes are very, very slow and not really noticeable, but this diagram here does a good job of showing that second law, where we have the equal area covered. So we can see there area Y, the long narrow slice here, is the same amount of area because it's so long and thin as area X, which is shorter and wider. Because the planet's moving a little faster here, in the same amount of time it's able to travel a little bit further, but it's much closer to the sun. Here, because the planet's moving slower but it is further away, we have the same amount of space if we think of cutting this up like a pie inside. So that's why it's covering an equal area. And then we have our third one here, the harmonic law. Harmonic law is the law where we find the relationship between the time it takes a planet to go around the sun in the sidal period and its astronomical units away from the sun. Now it's astronomical units. An astronomical unit is going to be the average distance from the Earth to the sun. So we're looking at how far these planets are away based off of the average distance of the Earth to the sun. And we get a very interesting kind of different relationship where we see that the planets have that odd relationship where if we square the time it takes them to go around the sun, it's going to be equal to if we cube their average distance from the sun. And then we start to get into Newton and gravity. So gravitation is a force of attraction between any two objects with mass. The strength of the attraction is proportional to their masses and inversely proportional to the square of the distance between them. Now, we have here the apple falling on Newton's head. It probably really didn't fall on his head, but he probably did witness an apple fall out of a tree, and it got him thinking about gravity, along with then thinking, if apples fall down, does the moon fall to Earth as well? And it got him thinking about gravity, and he then created his laws of gravitation and came up with his ideas on motion, along with developing calculus in his free time. And he developed the calculus as a way to explain gravitation and how objects fall to Earth. So in Newton's first law, an object's going to stay at rest or not want to move, and it's going to want to stay in motion, or if it's in motion, it's going to want to stay in motion. If it's at rest, it's not going to want to start moving, unless something else is going to come and act upon it. In Newton's second law, the more force we have applied to an object, the faster it's going to go. And in Newton's third law, for every action there's an equal and opposite reaction. And we gave some examples of them in class, but they're pretty straightforward. Then we get into Einstein, and Einstein does a great job of then taking what Newton did and kind of tweaking it and kind of cleaning it up. So Newton did a pretty good job of trying to understand this concept of gravity, which nobody else was really able to figure out or think about really before that. But Newton was never able to explain what gravity is, and Einstein's able to kind of explain gravity and come up with an even more accurate way of explaining this gravity. So Einstein proved that gravity is not just an imaginary force that pulls objects together, but through his theory of general relativity, he has found that it's going to bend the space around the objects and cause them to be pushed together. Okay, and we can see from this view we had a little model that we set up in the classroom. Through Newton, we could say that the two balls are attracted to each other, and they sense each other's presence. And because they sense each other, then they will be pulled together. But we see that that's a little bit different. If we look at a different view, we can think about the way that Einstein says that gravity works. So if we add some mass to the fabric here, we can see how it bends the fabric. And since it bends the fabric, we can see how the fabric kind of pushes the two heavy masses together. We did do a couple other demonstrations with this model. While we had it set up, we can look at how particles of light move in a straight line when no mass is present. So right there we have a particle. There's no mass on here at all, so that particle follows a nice straight line as it comes across. We did some other examples of then if we add mass, what happens. And we can see the way the particle moves then when it does have mass added in there and it's not in a straight line. And we can see this again from a different view as the particles go across the surface there in a straight line. And then you can see the curvature of light as that particle gets bent by matter. Okay, here we have another example where we're looking down and we can kind of see the way that the Earth and Moon would be able to follow each other around and then orbit the Sun. So as we get them going around, we'll have a larger marble representing the Earth and a smaller marble representing the Moon, and you can see the way as they go around that Moon will follow that Sun. Here we're going to see that again from a different angle, and it's a little bit easier to see. Now, to take notice, we can see that this fabric is actually bending a little bit with the marble as it goes around, and that's why the Moon will stay with the Sun. So that the Moon follows the Sun, I meant that the Moon follows the Earth as the Earth goes around the Sun. It's a little tough to tell, but from the angle above, you can't really tell that the fabric's moving. But if you look from underneath here, you can kind of see why that Moon would follow the Earth as it goes around, as the Earth is bending that fabric and the Moon is following it as it orbits around. So it makes it a lot easier to see that from this angle underneath. In this example, we can start to look at how the planets would go around the Sun. We can see that they're not perfectly circular orbits, and that they are kind of elliptical, and how they kind of speed up as they move in and then slow down as they get extended out. So those are a couple examples of a model that we set up in class. We did some other things with it as well, and we were able to explore how relativity works with the bending of space-time. So this kind of shows how light is bent in just a diagram, but we got to see that with the model that we looked at in class. And then we talked about how gravity is changed because time is relative in Einstein's theory when we talk about GPSs, and we read an article on how GPS clocks are different than the clocks on Earth, and it has a lot to do with their distance from the Earth and the speed at which they're traveling, and that affects the different speed that the clocks are, and they need to be corrected so that the GPSs work correctly in giving the directions for people on Earth. And I just kind of did a quick little overview of some of the things that Einstein did, and this was a nice little graphic to kind of show the importance of the different things Einstein did with space and time coming together in his special theory of relativity, and his E equals mc squared, with energy and matter coming together for his general theory of relativity. And we end it with this last note here where Einstein was finally able to show that gravity is really how large objects are affected in space. And he also developed the idea of space-time and how space is not always, or how time is not always the same everywhere. And that brings us to an end of this section. If you have any questions, feel free to stop by in class and ask.